for being here today. My name is Edward Chae, and together with my teacher, Jun Kweon, we are presenting our project titled IoT-Based Fruit Ripeness Detection using Computer Vision. This work aims to address a very practical challenge in agriculture using affordable technology. So the challenges of fruit ripeness detection. Let's start by understanding the problem. Traditional methods of checking fruit ripeness are either manual or destructive. Visual inspection depends on human judgments and can vary from person to person, while destructive testing wastes the fruits and cannot scale efficiently. To solve this, we developed a smart IoT device that uses computer vision to objectively and consistently evaluate ripeness through multi-feature image analysis. So the system, architecture, and hardware components. The slide shows the hardware structure of our system. At its core, the ESP32 CAM, a small but powerful microcontroller with a built-in camera and Wi-Fi, making it perfect for edge computing. To ensure consistent lighting, we use a ring light LED set at 5000K color temperature. The camera and the LED fix inside a 3D printing housing that maintains a 10 centimeter distance from the apple. For consistent image capturing, we can use LiPo battery to make sure the device is portable for field use. System workflow. Here is how the system works. After powering on, the device connects to Wi-Fi. The user then places the device over the apple, presses a button, the LED turns on, and standardized image is taken. The image is pre-processed to detect the apple's shape using the circular Hughes transform. We extract three key features: color, texture, and glossiness, and calculate a composite ripeness score. Finally, the results are sent to the server or app using the Wi-Fi protocol. Ripeness estimation, feature extraction. The core of our system is to feature extraction process. First, redness ratio is computed by identifying the red pixels in the HSV color space. Second, the texture entropy is calculated by grayness image to measure surface uniformity. Unripe apples, on average, are smoother, so they have a lower entropy. Third, the glossiness index checks how the light reflected from the apple's waxy surface is measured. Together, these features provide a reliable way to assess ripeness. Slide 6, composite score and classification. Using the extracted feature, we calculate a composite ripeness score ranging from 0 to 100. The weights for each feature were optimized using grid search to best match real Brix values. For Fuji apples, for example, we found the best weight to be 0.5 for redness, 0.3 for texture, 0.2 for glossiness. Based on the score, we can classify the fruit as unripe, ripening, or ripe. So the experimental results. We tested our system with 150 Fuji apples. Experts in digital refractometer determined the ground truth based on Brix level. We implemented the algorithm in MicroPythons using lightweight versions of OpenCV on the ESP32. Our system achieved an accuracy of 92.7%, and the correlation with Brix values was 0.88, showing that this method is both practical and accurate. The conclusion of future work. To conclude, we successfully demonstrated that a low-cost, non-destructive IoT solution can estimate fruit ripeness using computer vision. In the future, we plan to integrate lightweight CNN models like the MobileNet V2 to improve generalization. We also aim to move beyond classification to continuous predictions of sugar and acidity levels. Lastly, we will enhance outdoor performance with developing adaptive color correction algorithm for varying sunlight conditions. The setup experiment. The slideshow shows our experimental setup. The compact design and the simple operation make this device easy to use on fields or in storage facilities. It captures consistent images, and the entire process, from image capture to result transmission, takes just a few seconds. Thank you very much for your attention. If you have any questions, I'll be happy to answer them now. Yes, sir.